Hello.
Yes, madam. Yes, madam. You can go ahead.
Yes, sir.
Sir, with the permission of Subramania, sir, can we start the session now?
Hello? Yeah.
Can we start the session, sir?
Okay, okay.
Yes, sir. Yes. Dr. Meena, you can go ahead now.
Yes, sir. Sir, good afternoon all. This is a webinar regarding nanomaterials and their application, a bird eye view. I'm Dr. Meena, Assistant Professor, Department of Chemistry, Dayananda Sagar College of Engineering. I'm inviting you all for the session. And now I'm welcoming Dr. Anandaraju, sir, HOD and COE, Department of Chemistry, Dayananda Sagar College of Engineering, to welcome the speaker for the session.
Good afternoon to all. Myself, Dr. K. Anantaraju, Professor at Department of Chemistry. Professor Subramania, our beloved principal, Dr. B.G. Prasad, in his absentia. Fellow faculty members, faculty coordinators, Dr. Meena, Dr. Vinita, Dr. Arvind, and my dear students. Really, it gives me immense pleasure to welcome the gathering to the webinar on nanomaterials and their application, a bird's eye view. Before I'm going to start that, just I would like to highlight that the aim of this webinar is to give opportunity to the students and faculty members to make change in our lives in a meaningful way, so that by that we need to give it to the society. Definitely, this webinar is going to give real-time experiences, thereby bringing some innovative ideas so that we can exchange our critical thinking thought process to address the needs of the society. Saying that, just I would like to highlight to the students especially that you need to know that in the year 2020-24, recent breakthrough as through the nanomaterial is that which is very unique, that is nano lasers are there, and very fast what does that mean to say, a very important area where exactly we need to concentrate regarding nanosensors, and also these nanomaterials are used for targeting the cancers, display applications, as well as water remediation. There are many applications are there. So anyway, one of the module is there for the students, which is very benefit if you wanted to go and achieve your career, so that you can take this as a important breakthrough in your life. I would like to welcome today's eminent speaker, Professor Subramania from Pondicherry University. Sir, I am thankful for accepting your invitation to deliver a talk. Sir, on behalf of management, principal, and chemistry department, faculty members of the department, and students, I heartfelt welcome to this webinar session, sir.
Thank you, sir.
Last but not the least, hearty welcome to the faculty members and as well as the students for their interest and as well as the participation for this webinar program. Thank you. Have a nice day. Thank you, sir. Thank you very much.
Thank you, sir. Thank you so much. So followed by this, I would like to give the introduction about today's speaker. So again, let me give the introduction. I'm Dr. Meena, Assistant Professor, Department of Chemistry. Pleased to give the introduction about our eminent speaker, Dr. Professor A. Subramania, sir. He is the Dean Manjan School of Green Energy Technology, former Head Center for Nanoscience and Technology, Pondicherry University, Puducherry. Sir has received his PDF from Korea Institute of Science and Technology in 2008. He has received a Doctor of Philosophy from Alagappa University in 2001. His area of specialization in electrochemical science and technology, polymer science and technology, nanoscience and technology. As he has received many awards due to the time limit, I would like to highlight only few here. Dr. Subramania sir has recognized as world's top 2 scientists in 2022 till 2024. He got Ruler Award, which is International Best Scientist in Energy Conversion and Storage Material Developments in 2020. He has got Best Teacher Award, Best Research Poster Award, and Best Researcher Award in like many years. There is a number of awards. Along with that, he is an editorial member of many reputed journal as well. He has published more than 200 research papers, 11 patents, 12 book chapters in reputed publication. So has completed more than 13 projects under UGC and CSIR, etc. He is guiding as well as guided for PDF scholars, more than 24 PhD scholars. He has given research guidance, and he is presently giving for PDF students guidance. Along with that, he is guiding more than 100 students in MTech, MPhil students as well as in UG graduate students. As many more to say about him, but all our students are waiting to listen his talk. I will complete the introduction talk here. Professor Dr. Subramania sir, I welcome you for this talk, sir. Thank you.
Thank you, Dr. Meena, for the introduction about me. Very good afternoon, every one of you. I am very grateful to Dr. Prasad, Principal of Dayananda Sagar College of Engineering, Dr. Anandaraju, Head of the Department of Chemistry, webinar coordinators, Dr. Vinuda, Dr. Aravind, Dr. Meena, for their invitation to give a talk in this prestigious college. Dear students, now I am going to give a talk on nanomaterials and their applications, a bird's eye view. The objectives of my talk is to familiarize about nanomaterials and their properties, and various methods for the synthesis of nanomaterials, some of the characterization techniques, then besides that, some of their applications in energy conversion and storage devices, biomedical engineering, cosmetics, agricultural and food industries, textiles, water purification, and automobile industry. Let us see what is nanomaterials. See, nanomaterials is the study of materials at less than 100 nanometer in size. That is the size of atoms. 1 nanometer equal to 10 to the power of minus 9 meter. For comparison purpose, consider the width of human hair is approximately 1 lakh nanometer in size. From this, you can imagine how small it is. See, red blood cell has 7,000 nanometer in size, whereas white blood cell has 10,000 nanometer in size. Virus has 100 nanometer in size, whereas bacteria 1,000 to 10,000 nanometer in size. See, various the nanostructured materials are classified based on their size and shape as nanoparticles, nanofibers, nanowires, nanorods, fullerenes, nanotubes, graphene, nanoseeds, nanosprings, quantum dots, nanofluids, nanocore cell, nanoflowers, nanocubes, etc. See, some of the morphology of nanostructured materials are presented here. See, first one is quantum dots. See, quantum dots is the material as less than 10 nanometer in size. So it can easily grow even in the room temperature itself. Hence, the quantum dots always we have to keep in particular solvent. So here, what you are seeing is that gold quantum dots we have kept in the proper solvent. So then next one is nanoparticles. That is the morphology of nanoparticles. Then nanowires morphology. Then nanospring is like this. Then nanofibers. Then nanorods. This is the nanoseed. Example, graphene. Then nanotubes. Best example, carbon nanotubes. Then fullerene. The nanomaterials are classified based on the number of dimensions. So that is 1-dimensional materials, 0-dimensional materials, and 2-dimensional materials. Let us see one by one. What is 0-dimensional materials? See, in 0-dimensional nanomaterials, the length, height, and width are confined to the nanoscale, and hence it has 3-dimensional confinement. Example, quantum dots, fullerene, nanoparticles. Second one is one-dimensional nanostructured materials. So that means in one-dimensional nanostructured materials, both height and width only confined to the nanoscale, and hence it has two-dimensional confinement. Example, nanofibers, nanotubes, carbon nanotubes, then nanorods, etc. Then two-dimensional materials. In that, height only confined to the nanoscale, and hence it has one-dimensional confinement. Example, graphene, nano coating, etc. So three-dimensional means length, width, and height are not confined to the nanoscale, and hence it has zero-dimensional confinement. Example, bulk materials. So graphite, TaO2 in the bulk manner. Then synthesis of nanomaterials. There are two approaches involved in the synthesis of nanomaterials. So first one is top-down approaches. Second one is bottom-up approaches. So in the top-down approaches, from the bulk material, that is three-dimensional material, we can bring the two-dimensional or one-dimensional or zero-dimensional materials. So for example, let us take the graphite. Graphite is a three-dimensional material. It can be exfoliated, okay, into two-dimensional graphene-like structure. This two-dimensional graphene-like structure can be rolled up into one-dimensional nanotube-like structure, that is carbon nanotubes, or wrapped up into zero-dimensional buckyball structure, that is fullerene. So from the three-dimensional material, we can bring two-dimensional or one-dimensional or zero-dimensional nanostructured materials. Similarly, bottom-up approach, in that from the atomic level, so the molecules joined together will make into zero-dimensional or one-dimensional or two-dimensional materials. That is bottom-up approach. So from we are bringing the material into either one-dimensional or zero-dimensional or two-dimensional. That is bottom-up approach. The unique properties of nanomaterials. So nanomaterials are not just smaller than the bulk materials. At the nanoscale, fundamental properties will change tremendously. Its chemical reactivity greatly differ from the macroscopic materials. For example, nano gold. When we reach into nanoscale, the color, melting point, and chemical properties of nano gold changes due to its interaction among their atoms. Nano gold does not like bulk gold. It can be orange, purple, or violet depending on their size. So at the nano level, the electrons will not move freely like in bulk gold. Its energy gap increases with the reducing in particle size. Hence, the nanoparticles react differently with the light, and thus we are observing different color. Then surface area. See, the total surface area of nanomaterials increases on reducing the size of nanomaterial due to increase in surface to volume ratio. Similarly, the melting point of nanomaterials decreases considerably as the size of nanostructured material decreases below 100 nanometer. See, when we reducing the particle size, surface energy increases. Due to that, the melting point decreases. Hence, the bulk gold has the melting point of more than 1400 degrees centigrade. Whereas if it is nano, okay, the melting point is less than 750 degrees centigrade. Then band gap of nanostructured materials. The band gap of nanomaterials increases as the size of nanomaterials decreases. Then synthesis of nanostructured materials. Okay, many methods are available to synthesis different types of nanostructured materials in the form of particles, wires, rods, tubes, or thin films, or thin sheet-like, etc. So the most important and simple methods are given here. See, if you want to prepare the quantum dots, that is less than 10 nanometer in size of materials, you have to go for hot injection method. Then nanoparticles with 10 to 100 nanometer, for that you can go for either dilute precipitation or combustion, sol gel, or biological method. So then nano wires and nano rods, that is one-dimensional materials that can be prepared by using hydrothermal, solvothermal, or template assisted or electrospinning technique. We can use to prepare one-dimensional nanostructured materials. Then two-dimensional nanostructured materials can be prepared by sonochemical exfoliation or microwave exfoliation or electrochemical exfoliation method. So depending on the interest of the nanostructure, we have to choose the method of synthesis. Then see, biosynthesis or green synthesis. In this, by using plant extract or selected microorganisms such as bacteria, fungus, or algae, we can prepare nanoparticles. A typical example for the synthesis of metal nanoparticles from plant extract is given here. See here, the plant extract was mixed with the metal salt solution and then kept at specific reaction conditions to get metal nanoparticles. Here, by optimizing the pH and concentration of the extract, reaction time, and temperature, we can get the nanoparticles. Then another interesting technique is electrospinning. So by make use of this technique, you can prepare one-dimensional nanostructured materials in the form of either organic, inorganic, and hybrid material can be easily prepared with the dimension ranging from nanometer to micron. So metal oxides, nanofibers such as TiO2, zinc oxide, zirconia, etc. can be prepared by using this technique. The formation of the nanofibers depends on the polymer molecular weight and concentration, then solvent, then viscosity, then process voltage, distance from the needle to substrate, then flow rate of the electrolyte, then relative humidity, temperature. So based on that, the formation of the nanofiber is there. So if we use a simple needle type spinneret, we can get the wire or fiber-like materials. Instead of using coaxial spinneret, we can get the hollow or core cell kind of nanofibers we can prepare by using this electrospinning. Here, a typical synthesis for the synthesis of TiO2 nanofiber is given here. So by using this electrospinning technique, by applying the DC voltage of 15.3 kilovolt, we can get the electrospun TiO2 mat-like materials. That mat-like materials, by calcination at 470 degrees centigrade for 5 hours, we can get the TiO2 nanofibers. So the calcination temperature can be predicted by using this gravimetric analysis. So here the weight loss versus temperature. So curve is presented here. So here the beyond 470 degrees centigrade, there will be no change in the curve, the thermogravimetric curve. So that means that is the required or optimum temperature to calcination for the calcination of the prepared mat to get the TiO2 nanofiber. This is the XRD pattern of calcined TiO2 nanofibers. The presence of 101 peak confirms the formation of anatase peak. Then the sharp peak indicates the crystalline nature of the materials. Its crystalline size is 11.36 nanometer. See, this is the TEM image of TiO2 nanofibers. So here the TiO2 nanofibers are packed with a huge number of TiO2 nanoparticles of size less than 50 nanometer in size. That's why by using this technique, you can prepare interlinked, highly porous materials. Then applications of electrospinning. So by using this electrospinning technique, so we can prepare the nanofibrous membrane, so that can be used for tissue engineering applications, drug delivery or wound healing, dressing materials preparation, military protective cloth, then enzyme carrier, we can use this, then nanosensors and energy conversion and storage devices, we can use this electrospun membrane. Then sonochemical exfoliation method. So in this method, the bulk molybdenum selenide nano powder undergone exfoliation into molybdenum selenide nano sheets like structure using hydrogen peroxide as an exfoliating agent. This reaction mixture was subjected to sonication at 500 watt for 30 minutes in a ice cold condition to get molybdenum selenide nano sheet. So here the intensity of 002 peak is reduced and broadening from the unreacted one indicate the formation of highly exfoliated molybdenum selenide nano sheets. Then the position of this T1G peak and the intensity of this E2G peak are confirm the formation of few layers. Then here the A1 peak position shifted to lower wavelength, okay, that is red shift, and the intensity of E2G peak is reduced, which indicate the formation of molybdenum selenide nano sheets. Then the intensity of this 002 peak is reduced and broadened from the untreated one, indicates the formation of highly exfoliated molybdenum selenide nano sheets. So this is the FESM image of molybdenum selenide nano sheets for 15 and 30 minutes of sonication time. In 15 minutes of sonication, that is not sufficient. That is why the straked layer of molybdenum nano sheets are observed, whereas at, at 30 minutes of sonication, a few layers of molybdenum selenide nano sheets are observed. By using this AFM, that is atomic force microscope image, you can measure the how much number of layer present after exfoliation. So that can be predicted by using this AFM technique. Then electrochemical exfoliation method. See, by using this simple electrochemical exfoliation method, you can prepare graphite from the graphite to graphene. So for that, you have to use graphite rod as the positive anode, platinum plate as the negative electrode. So these two electrodes immersed in 1 mole sulfuric acid. So by applying the 15 volt, okay, for 30 minutes, so that graphite will undergo exfoliation to get the graphene at the cathode as deposit. From that, you can collect and vacuum dried at 70 degrees centigrade for 12 hours. Here the high intensity of 002 peak at 26.7 and a small intense peak. Okay, this one 55.1 degree confirm the natural graphite. This is the XRD pattern of natural graphite, whereas this one graphene. So here the 002 peak, okay, that is sharp and very low intense peak comparing with this one graphite, and appeared at 26.7 and a small broad peak. So here the very thin peak is there, but here broad peak is there. So that indicates the formation of exfoliated graphene. Then some of the characterization techniques, okay. generally we are using for in the nanomaterials development. So first one is TGDTA. The phase formation under complete crystallization temperature can be predicted by using this TGDTA analysis. X-ray can be used to know the phase purity or structural conformation or crystallite size determination of the material. Then FTIR can be used to know the structural conformation. Then UV visible used to know the optical properties of the materials. PL used to know the optical properties of the materials. Laser Raman can be used to structural conformation. In particular, two-dimensional material, this laser Raman or micro Raman is very useful. Then FESM can be used to know the surface morphology and the average particle size of the prepared nanomaterials. Then EDX used to know the elemental composition of the materials. Then HRTM used to know the particle size and microstructure of the materials. Then diffused reflectance spectroscopy. So by using this band gap of the semiconductor materials, we can easily identify it. Then BET, so specific surface area and pore size and pore volume of the materials can be predicted. Then dynamic light scattering technique used to know the particle size and zeta potential of the material. AC impedance technique used to know the charge transfer resistance, double layer capacitance and ionic conductivity of the materials. Then let us see the applications of nano materials in energy devices. First one is, let us see nanomaterials in solar cell. See, photovoltaics or solar cell is a device used to convert the harvested sunlight into the electrical energy. So in the market, different generation solar cells are available. First generation solar cells are silicon vapor based solar cells, that is based on monocrystalline silicon or polycrystalline silicon. They are non-flexible with a high manufacturing cost. Even then, this type of solar cells are still dominating in the market due to their high efficiency. Then second generation solar cells are thin film solar cells, that is based on amorphous silicon or cadmium telluride kind of thin film based one. They are flexible, significantly cheaper, but having much lower efficiency. Then third generation solar cell, that is nanomaterials based solar cells. So example for these solar cells, dye sensitized solar cell, quantum dot sensitized solar cells, then organic photovoltaics, perovskite solar cells. So these are all some of the examples for third generation solar cells. So the advantage of this one is simple fabrication process, flexible, relatively low cost. A typical dye-sensitized solar cell consists of photosensitized dye-adsorbed wide band gap semiconducting metal oxides, that is made up of TiO2, tin oxide or zinc oxide, used as the photoanode, then platinum thin film used as the photocathode, then iodine iodide redox couple used as the electrolyte. Okay, so this is the setup of dye-sensitized solar cell. So instead of using the N719 dye, that is ruthenium based dye. So instead of this is very costly one, instead of that, we can also use quantum dots. Okay, so inorganic quantum dots such as silver selenide, zinc selenide, or zinc sulfide, like that we can use as a sensitizer. So if we use these kind of materials as a sensitizer, that solar cell is called it as quantum dot sensitized solar cell. So the advantage of quantum dot sensitized solar cells is when we use quantum dots, that can create a wide solar spectrum. That is the advantage. So, but in dye-sensitized solar cell, limited solar spectrum is there. So thus the quantum dot sensitized solar cell will work even at the very low intensity light. Then let us see the advantages of dye-sensitized solar cell over conventional solar cells. See, in conventional solar cells, ultra-high pure materials are required, whereas quantum dot sensitized or dye-sensitized solar cell, ultra-high pure materials are not required. here the charge separation takes place in the same material, and hence charge recombination is high, whereas here the charge separation takes place in two different materials, and hence charge recombination is low. Here the so conventional solar cell, for that it required high process and material cost, whereas dissociated solar cell, to make this, the processing cost is very low, and material also very cheaper material here we are using. So hence the cost of the DSSC is 1/10 of silicon based solar cell. So these are some of the applications of dissociated solar cell. So we can use this dissociated solar cell to make the flexible lightweight charger, power cloth, then window glasses and roofs we can easily fabricate to get the power, then mobile charger, then solar jackets we can make by using this dissociated solar cell. Then rechargeable lithium-ion batteries. In that, there are two kinds of rechargeable lithium-ion batteries are there. First one is lithium batteries, another one is lithium-ion batteries. So how these two batteries differing? So based on the anode. See, when we use lithium foil as the anode, that battery is call it as lithium battery. When we use graphite as the anode, that battery is called it as lithium-ion batteries. So that is the difference between lithium battery and lithium-ion batteries. So generally, lithium cobaltate, lithium magnate, lithium iron phosphate, can be used as the cathode material in lithium-ion battery or lithium battery. Both we are using same cathode materials. So, but if we prepare these materials in the nano manner, nano particle like, so we can increase the efficacy of the battery and the lifetime of the battery. So advantages of lithium-ion batteries, and then the other conventional batteries is given here. See, high voltage battery, lithium-ion batteries are high voltage, whereas lead-acid battery, that voltage is one cell voltage is 2, whereas here the minimum cell voltage is 3.7 volt. Then high energy and power density battery, then longer cycle life, then minimum self-discharge, then no electrochemical redox reaction taking place in this. That's why the lifetime of lithium-ion battery is more than 5 years. So here the mechanism behind this lithium-ion battery is charge-discharge occurring by intercalation of lithium from the anode to cathode. These are some of the applications of lithium-ion batteries. So electric vehicle, laptop, the MT players, candy recorder, personal computer, cellular phones, digital cameras, all these nowadays we are using lithium-ion batteries. Then next one is supercapacitors. Supercapacitors are electrochemical capacitors, act as booster to batteries and fuel cell in hybrid electric vehicle to provide necessary extra power for acceleration. The supercapacitors have high power density with moderate energy density, whereas the battery has high energy density with moderate power density. That's why we have to use this supercapacitor to boost up the power density of the batteries and the fuel cells. There are 3 types of supercapacitors are there. First one is double layer capacitors, pseudo capacitors, then hybrid capacitors. In double layer capacitors, both electrodes are made up of carbon based one. Here the electrodes are made up of metal oxides or conducting polymers, whereas in hybrid supercapacitors, both carbon and conducting polymers or metal oxide based electrodes are used. That's why called as hybrid supercapacitors. These supercapacitors also used in electric vehicles, handy camera, computers. Then applications of nanomaterials in medical field. So nanomaterials can be used to deliver medicine or drugs into a specific part of the human body, thereby making them more effective and less harmful to the other parts of the body. So gold nanoparticles are being used in drug delivery, drug discovery, and drug formulations. CNTs are being used in encapsulating drugs for drug delivery. The nano scaffold. So nano fabrics, okay, obtained from this electrospinning technique are used as a scaffold for tissue and organs regenerations. They are also used in bone implantation and bone tissue engineering. Then nano robotics. Okay, these nano robotics are nanoscale devices used to enter into the body for diagnosis and treatment. They are used in early diagnosis and to perform the nanosurgery without open surgery. Further, they used to perform treatment on cellular basis. See, when we use nano quantum dots, okay, okay, so that in molecular images we can see very nicely. So nano materials we can use for bioimaging applications. Then nano cells, okay, that kill the tumor cell selectively. So for that also we can use this nanotechnology. Then wound healing and wound dressing materials. So electrospun membranes are used as wound healing or wound dressing materials. They possess antimicrobial properties that helps to prevent the wound infection. They can also used as a drug delivery system for chronic wounds and other injuries. They can release the drugs in a controlled and sustained manner to promote wound healing more more easily. Then applications of nanomaterials in cosmetics. So nanomaterials are being used extremely in cosmetic industries to improve their quality. The nanoparticles are used in shampoos, conditioners, toothpaste, then anti-wrinkle creams, moisturizers, face powders, shave lotions, deodorants, sunscreens, makeups, nail polish, etc. They provide deeper skin penetration, long-lasting effect, and to increase the color and the quality of the products. Then sunscreen lotions. See, in sunscreen products, zinc oxide or TiO2 nanoparticles are being used to protect the skin from UV rays. When we apply a conventional sunscreen that leave a white sticky layer on the skin, this can be avoided by using nanoparticles in the sunscreen lotion, so that we can make a transparent and non-sticky sunscreen lotion by using nanoparticles. These nanoparticles can block the UV rays to protect the skin from UV rays. Then anti-aging cream. So generally the quantity of collagen in the skin decreases with age. It plays an important role in skin regeneration. So nanoliposomes and fluorine C60 are being used to produce anti-aging creams. Here C60 act as a potential scavenger for the removal of free radicals. Then lipsticks and lip gloss. So here the silica nanoparticles are incorporated into lipstick and lip gloss to soften the lips and to maintain the color for a long period of time. They also prevent the pigment bleeding from the lips. So iron oxide nanoparticles are used as a pigment to make shiny lip color. Then moisturizer cream. See here in this, the nano gold or nano silver are being used to produce non-sticky moisturizer creams. These nanoparticles can penetrate deeply into the skin and deliver nutrients to the skin cells most effectively. Then let us see the applications of nanomaterials in agricultural and food industry. See, in agricultural, CNTs are carbon nanofibers are being used to improve crops growth. They are used to improve the germination of seeds through better penetration of moisture into the soil. See, this one CNT untreated soil, so it has given lesser growth, whereas this one soil is treated with CNTs, hence it has given more growth. Then the nanoparticles are being used to facilitate germination of seed growth. See, this one is zinc oxide nanoparticles, untreated seed, so hence its growth is less, whereas this one, these seeds are treated with zinc oxide nanoparticles, hence it has given more growth. Then silver and copper nanoparticles are being used to reduce fungal diseases on a perennial grass. The nanofertilizers. So nanofertilizers are being used to enhance the productivity of crops by taking the nutrient more effectively. See, this is the groundnut plant. See, here we used conventional fertilizer. Due to that, so the yield is very poor. Here we used nano fertilizer. So due to that, the yield we got little higher. So self-life improvement. So self-life of fruits and vegetables are being extended by using nanoparticles. For example, zinc oxide nanoparticles with citric acid incorporated electrospun membranes are being used to improve the self-life of mangoes and bananas. Here citric acid is used to preserve the color and the texture of the fruits. See, this banana is untreated banana, so does not retain its originality after 50 days. See, this one fully protected bananas, so retain its originality by using this nanofibrous membrane. Then oxygen scavenger films. So nanosilica and TiO2 particles embedded packaging films are being used as a oxygen scavenger to avoid food spoilage by aerobic microorganisms. Then incorporating nanoparticles with this antimicrobial properties, okay, in some reusable food containers, refrigerators and freezers to maintain the hygienic condition inside them. Then intelligent packaging. The nanosensors are being used in food packaging to detect spoilage of food products. It gives the information about the storage period of packed food. Then let us see the applications of nanomaterials in textiles. So inclusion of 5% nano clay in nylon 66 is used to increase the tensile strength and flexural strength of the fabrics. Further inclusion of nano clay with flame retardants has improved the flame retardancy of the synthetic fabrics. Then nanoparticles are being used to make stain resistant finishes. They can also be used in making textiles with natural feel and breathe for a longer time. Then self-cleaning or water repellency effect can be made in the fabrics. So for that, the water repellent properties of the fabrics is created by some fluorinated chemicals. In particular, short chain fluorinated chemicals offer superior propellant performance than long-term fluorinated chemicals. See, the non-fluorinated chemical such as paraffin, silicon, stearic acid, and melamine are also used to provide water repellency. The hydrophobicity. The hydrophobicity of a surface can be measured by its contact angle. See, higher the contact angle, the higher the hydrophobicity of a surface. Surface with a contact angle of less than 90 degrees centigrade is performed to referred to as hydrophilic, and those with an angle of greater than 90 degree is referred as hydrophobic. Some plants show contact angle more than 160 degree and are called super hydrophobic. Example, lotus leaf. So super hydrophobicity can be obtained by making roughness on the fabric without affecting the softness of the cotton fabrics. So hydrophobic property can also be created on cotton fabric by coating a thin nanoparticle plasma film. Then the fibers containing 3 weight % of nanosilver is used for food odor elimination and food infections. Then antimony pentoxide nanoparticles with halo compounds are used for flame retardant finishing. Then antimicrobial textiles. Some organosilicons, phenolic compounds, then bisphenolic compounds have antimicrobial activity which will eliminate infection, odor, itchiness, and sores from the fabrics. Then nanosilver, TiO2, zinc oxide, then hydrogen, etc. are also used to impart the antimicrobial properties to the fabrics. Then protective textiles. So CNTs are being used in electromagnetic wave absorbers, gas sensors, field emission devices, etc. CNTs based filtering cloths are used to eliminate heavy hydrocarbons from the petroleum in a single step filtering process. Then lightweight bulletproof vest. So most of the bulletproof jackets and exfoliation proof blankets are being made with Kevlar. Kevlar is a kind of polymer, that is polyparaphenylene terephthalamide, is a heat resistant and strong synthetic fabrics. So further, the ultra high molecular weight of polyethylene fabrics with graphene are being used to make impact helmets. For body armor, high pure alumina, silicon carbide, and boron carbides are being used. CNTs can also be used to produce nano fibers with 100 times stronger than steel. Hence, the CNTs are used in bulletproof armor. Then applications of nanomaterials in water purification. So contaminated water produces some diseases such as malaria, cholera, typhoid, then viral fever, skin diseases, goiter, etc. Hence, the drinking water should be purified. So purification can be done by nano-adsorbents or membrane technology. In nano-adsorbents, metal or carbon-based nano-adsorbents are widely used in water purification. The carbon-based nano-adsorbents are used in drinking water purification process. They have the ability to improve the water quality by removing disagreeable taste and odor. Then metal-based nanoadsorbents are used to remove dissolved pesticides, pesticide residues from the soil. Then heavy metals such as lead, mercury, cadmium, nickel, etc. can be removed from water by using humic acid coated magnetic nanoparticles. By using this, we can remove the heavy metals from the water. In membrane technology, nanofibrous membranes and biologically inspired membranes are used for water purification. The electrospun nanofibrous polymeric membranes are used in water purification, whereas the nano zeolite or CNTs impregnated electrospun nanofibrous membrane are used to remove organic pollutants. In biological inspired membranes, antimicrobial materials such as nano silver or nano copper embedded electrospun nanofibrous membranes are being used to reduce biofouling odor from the water. See, the first one is polluted water containing E. coli, whereas this one, the polluted water with E. coli in the culture plate, whereas this one, the polluted water filtered through the nanofibrous membrane. So this is the filtered water. After that, we have, see, there will be no E. coli in the culture plate. So by make use of this electrospun nanofibrous membrane, we can eliminate the microbes from the water. Then electro nanocoagulation is the removal of total suspended solids, so emulsified oils and greases from the wastewater without the addition of any coagulating agents. So commonly used electrodes are aluminum or iron. So when applying an electric current, it forms their nano oxide and then converted into their nano hydroxides that act as a nano coagulating agent to remove the suspended solids from the water. Then electro-defluoridation is the removal of fluoride content less than 1 ppm in the drinking water by using electro-nano coagulation method. So in this process, when applying an electric current through aluminum electrode, it forms nano hydroxides. These nano hydroxides can have a tendency to entrap the fluoride ions so that we can remove the fluoride from the drinking water. If the fluoride ion concentration is less than 1%, okay, that promotes the dental health. Whereas if the fluoride ion concentration is 1 to 4 milligram per liter, okay, 1 to 4 ppm, that will create the dental fluorosis. Whereas if it is the concentration is more than 4 ppm, that will create the skeletal fluorosis. See, this is the fluorosis affected people. See, if the fluoride content is more than 1%, 1 ppm, that will create dental fluorosis. If it is more than 4 paper, that will create, okay, skeletal fluorosis. This is skeletal fluorosis. See, this is the fluorosis affected areas. See, the red spot indicating the severely affected areas in India. Then applications of nanomaterials in automobile industries. So metal matrix nanocomposites is the incorporation of nanofillers such as TiO2 or zirconia, silica, ceria, CNTs, graphene, boron nitride or silicon carbide, okay, into the pure metal. That is called metal matrix nanocomposites. This metal matrix nanocomposites should have improved properties such as microhardness, wear resistance, corrosion resistance than the pure metal. So the metal matrix nanocomposite can be obtained by using any one of the following method. First one is powder metallurgical method, then melting and solidification method, then thermal spray or electro deposition technique or other novel techniques such as sputtering, then sandwich processing or vapor deposition. We can make metal matrix nanocomposite. This is the surface, morphology of pure nickel. This is nickel ceria. This is nickel ceria nanoparticles embedded composite coating. So here the micro hardness of the electrodeposited materials or micro hardness of the metal matrix composite can be predicted by using this static indentation method. So see, the pure nickel has the Vickers micro hardness of around 280, 290 like that. Okay, whereas the this nanoparticle embedded one has higher micro hardness than the pure one. Similarly, the wear resistance. See here the friction, the wear weight loss and the friction coefficient of this one is around, see, less than 0.3 milligram than the pure nickel. So the pure nickel has around, see, nearly 2.5 milligram weight loss is there, wear loss is there, whereas the composite material has less than 0.3 milligram. So that means these material has very good wear resistant property. Then corrosion resistant property of the nano composite materials. See here the pure nickel, okay, has the charge transfer resistance around 306, okay, ohm per centimeter square, whereas this composite material has, okay, very high charge transfer resistance than this pure nickel. Hence, that implies that this composite material has very good corrosion resistant property. Then Tafel polarization we have taken for this composite and pure nickel metal. So pure nickel metal, nickel has the corrosion resistance around 17.6 microampere per centimeter square, whereas this nickel Syria embedded composite has corrosion current very less than the pure nickel. So it implies that it has high corrosion resistance. Hence, its corrosion rate is 3.84, okay, millimeter penetration per year, whereas this one 1.06 millimeter per year. Similarly, the CNTs or graphene reinforced metal nanocomposites can also be developed to increase the tensile strength and the elastic modulus of the composites. So this is the pure nickel, whereas this one nickel CNT embedded one, this one nickel graphene embedded composite coatings. See here also the comparing with the pure nickel, this composite coating has very high micro hardness of around more than 60 HV than the pure nickel. Then wear loss, then wear resistance. Okay, so taper abrasor tester we used to know the wear resistivity of the material. See here also the composite material has a wear loss of around less than 0.25 milligram than the pure nickel one. So pure nickel almost 2 milligram wear loss is there. Then corrosion resistance. So by make use of impedance technique, we have measured the corrosion resistance of the composite materials. See here also this graphene embedded nickel has very high corrosion resistant, charge transfer resistant than the pure nickel. Then this nano composite material has very least corrosion current than the pure nickel. It indicates that, okay, the composite material has very good corrosion resistant property. Then some of the applications of CNT's reinforced nickel nanocomposite coatings are given here. See, in automobile industry, okay, braking shoes, piston rings, gears. So all these things we can make by using this composite materials. So then aerospace industry, aircraft brakes and landing gears we can make due to its high wear resistance and high strength. Then sports industry, lightweight bicycles, then badminton racket, then tennis rackets we can make by using this composite material. Other industrial applications of nanocomposites are given here. See, wear resistant material if you want to make, so silicon carbide or alumina or tungsten carbide embedded nickel composite coating you have to make, or dry lubricant materials. So Teflon and molybdenum sulfide, mica, graphite embedded nickel can be used as for making this dry lubricant materials. Then nuclear control materials, okay, that can be obtained by co-deposition of neutron absorbing nanomaterials like boron and its compounds with nickel, so that we can make this nuclear control materials. Then corrosion resistant applications. For that, we have to do the co-deposition of silicon, alumina or TiO2 along with zinc. That will give better corrosion resistant. So in summary, the nanomaterials are driving innovations across various fields. from energy storage and medicine to environmental sustainability and electronics. So their unique properties at the nanoscale open up endless possibilities for technological advancements. Hence, exploring the nanomaterials will pave the way for a more sustainable and advanced future. That's all. Thank you for your attention. If you have any questions, you can ask.
Thank you, sir. It was a wonderful session. Students, if you have any questions, you can put it in Q&A session so that we can see your questions and we can answer regarding the session. Students, you can drop your questions in the Q&A box related to the session related to the application of nanomaterials. If there is any questions, you can drop down the questions in Q&A box.
Any questions?
Subramania sir.
Yes, sir.
So it was a nice presentation covering whole aspect, especially starting from some of the characterization to various applications. Especially,
Sir,
I
your voice
don't
is
know because in one of the. Oh, is it so? Okay. I'm audible, madam, now. Hello. Hello.
I couldn't be able to hear your voice, sir.
Now is it okay, sir? Is it audible? Amina, madam. Hello. 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 Hello.
Hello, sir.
Am I audible, sir?
Now only. Okay, sir.
Yes, sir. The presentation was very clear, especially starting from some of the characterization of the nanoparticles, and clearly mentioned various applications of these materials, sir. So, but one of the things, because in one of the slide you mentioned regarding utilization of this nanocarbon in the field of agriculture.
Yes, sir.
In the field of agriculture, sir.
Yes.
In the field of agriculture, but they're not so toxic, sir. So just
no, sir. That is carbon nanofibers we are using.
Them.
See, carbon in the form of nano, when we use
in the growth of the agriculture,
it is non-toxic, sir. Carbon only we are using, so non-toxic.
Okay.
Sir, suppose if you want to increase the iron content in the plant, we can use iron nanoparticles so that we can get the iron enriched plant, so that we can, when we intake, we can get the iron content. So iron deficient people, instead of taking tablet, okay, we can take naturally this natural one.
Okay, it's interesting, sir. Anyway, after the production of those vegetables or whatever it is there, we need to weight it with respect to the ppm level or the measurement of the content of iron or the any other carbon compared to the natural one. That we need to weight according to my knowledge.
Yes, that research is going on, sir.
Yes, sir. Good work, sir. Really good work.
Okay. In Canada, a lot of work going on in this regard, sir.
Thank you, sir. Thank you.
Lifetime of self-life improvement of fruits and vegetables, all these things.
Okay.
Any other questions?
Sir, almost we have received all the details, sir. Thank you for the information.
Okay. Okay.
Now I would like to invite Dr. Arvind sir for giving vote of thanks.
Good evening, everyone. I am Dr. Arvind Nesargi, Assistant Professor, Department of Chemistry, Dayananda Sagar College of Engineering. I'm going to give the vote of thanks for the webinar. First, I would like to thank the management, secretary, and the principal, sir, for their support to the conduction of webinar. I would like to mention special thanks to the HOD Professor K.S. Anantaraju, sir, for his continuous support and encouragement. I would like to express my sincere thanks to our today's speaker, Professor Subramania, sir, for accepting our invitation and given one wonderful talk for our students and faculties. The session gave the insight about classification, synthesis, properties, and various application of nanomaterials. The session helped to enlighten the knowledge regarding nanomaterials and its applications to our students. Last but not the least, I would like to thank all the students who have participated eagerly for the session. Finally, I thank all the faculty members who helped us to successfully conduct the session. Thank you.
Okay. Thank you. Thank you, sir.
Subramanian sir,
Finally, I
thank you very
would
much, sir.
like to say thanks to Dr. Arvind
Thank
sir,
you,
and
thank you.
especially here Dr. Vinita madam. Due to some emergency, she could not be here because she is the main person who has introduced you for this session, sir. And thanks to Vinita madam, I'm very much thankful to her and Dr. Arvind sir, who has helped me to organize this session. Thank you, sir.
Okay. Thank you. Thank you for the opportunity. Thank you.
Yes, sir.
Thank you, Subramanian sir.
Thank you. Thank you, sir.
We'll meet you, sir. Thank you, sir.
Sure, sir.
Thank you, sir.
Okay, sir.
Sir, we are ending up the session, sir.
Yes, ma'am.
Yeah, thanks. Sir,
Okay.
we'll text you, sir.
Okay, ma'am.
Thank you, sir.
Okay.
India, sir, please kindly close the session, sir.